Part of what I do is to take experiments around the country and try and enthuse physics teachers to include little short tricks to try and grab the attention of their classes, demonstrating physics in an enjoyable and enthusiastic way.
Today, David Richardson has been invited to demonstrate some of his physics experiments to staff at St James's Catholic High School in North London. Most of the staff at St James's are chemistry or biology specialists, so they're keen to get ideas from David that they can use with their students.
We usually have inset training sessions where people will observe someone carrying out a demonstration. This gives them a lot of ideas to be able to use these demonstrations in practical work.
Today, David has been asked to concentrate on forces and air pressure.
I need some help here, please. Wendy, would you like to come and give me a hand with this? Okay, ready. Quick, whenever you're ready. Good. And close it back up again. And, I'd start off a Year 7 lesson on forces, wouldn't even say anything at all, just walk into the classroom, plonk it on the front and set it up like that. And it's amazing how the kids are going, what's going on there, sir? And you try and explain anti-gravity paper. And they don't believe that. And then you link into a lesson on forces, onto turning moments, centre of mass. Because what's inside is, in the corner, is a big weight. And the rest of the box is empty.
Right, what I want to show you first is my magic box.
A couple of weeks later, Richard King, head of physics, tries out some of these experiments with his Year 7 group.
Right, I want to put it on this chair. Do you think it's going to be all right on this chair?
No. Yeah, put it on.
If I put it on a bit like
put it on properly.
that.
No.
Is it going to fall off?
No, yes.
Do you think it's going to fall off?
Yes.
What's going on? Can anyone explain that to me, please? Holly?
The air resistance is acting upon the box and then
Right.
acting in the air.
Right, you've got some good ideas there. You're thinking about air resistance, which is important, but don't forget air resistance only happens when something is moving. It's not moving. I tell you what, there might be something in the box which should help us. Maybe it's that. Is that what's keeping the box up?
No.
Why not? It's a helium balloon. It's pulling upwards. Is that strong enough to lift our box up?
No.
So what must it be then? Fernanda, what do you think?
There's something really, really heavy pushing down on the chair, so the box will stay up.
There's something heavy pushing down on the chair. If I turn the chair around like this, it doesn't look like the box should stay up, should it? No. Where do you think that heavy object is? In the corner. You lot are geniuses.
For the next experiment, again, this is about air pressure, and all you need is some marshmallow sweets, a clear wine bottle and a wine preserver. And if we have a volunteer, it is as simple as taking one of the marshmallows, rolling it in your hand so it's thin enough to put into the neck of the bottle. You build that up until you've got about half a bottle full of marshmallows. If you don't roll them between your hands, you can't get them in the top, but rolling them means they're thin enough to put, and they pop straight in. The next part is to take the wine preserver, to put it in the top of the bottle, and to remove the air using the pump. Now, the bit to encourage the pupils to watch is the size of the marshmallows as you suck the air out. And as you take the air out, you can see the marshmallows start to increase in size. Giving the bottle a shake will just give them room to expand. Reducing the pressure on the outside of the marshmallows allows the bubbles in the marshmallows to get bigger and expand, and you can quite noticeably increase the size of the marshmallows.
After David had been to see our teaching staff, they were very excited, and we thought, okay, we can do some of this in our school. So we got the sheet from David and adapted it to our way of preparing things.
I've got some marshmallows. Now what I'm going to do is I'm going to make some giant marshmallows. Suma's going to try and...
Suman, our physics technician, adapted some of the things like the pump for for the marshmallows, for example, we've actually done it with just a pump action and a conical flask with a side arm.
I was pleased we got it to work because the problem we had was the pump. We didn't have a two-way valve, so we had to kind of engineer a valve.
Can you make it blow up? Can you make them like go?
And letting the air back in, 1, 2, 3, and
Excellent.
And very lastly, when we get the air back in, there we go. You've got to think about what has happened here, guys, what has happened here, and therefore what is happening inside here. Someone said something about there being air inside marshmallows. That's what I want you to think about, okay? We're not going to talk about it now, you're going to think about it when you sit down.
I think it's the simplicity of some of the experiments that make them all the more effective. The simplicity of pumping some air out of a bottle and seeing what happens to marshmallows, that I know grabs children's interest. And when they see that happening, they want to know, well, why? Which is a lot more effective than some of the other more scientific demonstrations that we might do to show air pressure.
For this next experiment, you need a glass of water filled to the brim and a very thin cotton handkerchief, and have it so it's wet all the way round. You can get that to stick to the side of the glass, and you can, if you get it set up right, turn it upside down and then completely let go. It is possible to hold that over somebody's head, because we all completely trust the laws of physics. If you'd like to put your head under and demonstrate that the laws of physics are completely reliable. And then just to finish the experiment, you peel it off and show the water goes everywhere.
Thank you. I have to make sure it's there.
You'll run through, so you really want to do that.
Lift your head forward, please, Carl. And there we go. We've got the glass upside down above Carl's head. And is he getting wet? No. It must be magic, mustn't it? No. All right, Carl, move your head, please. Right, I'm actually not even holding the cloth now, and it's still working.
So when the handkerchief gets wet, why doesn't it start to seep through, the water seep through the handkerchief?
Well, I've heard two alternative explanations. The first one is that when you've got the handkerchief over the surface, it's the surface tension between each of the threads and the tiny holes holds the water inside. Combine that with the idea of you've got air pressure pushing upwards, holding the liquid in, and that's why the water doesn't come down. It's a combination of the surface tension between the threads and the air pressure inside. The next experiment again uses the idea of air pressure, but builds on that by using a Cartesian diver. To make a simple one in the classroom, all you need is a plastic drinks bottle filled with water and a combustion tube which is about half full with water. If you then invert that into the top of the lemonade bottle, you'll see that the combustion tube will float at the top. If you then put the top on the bottle, you can squeeze the sides, watch the air bubble get smaller. As it gets smaller, the tube sinks to the bottom. As you release the pressure, it rises back to the top again. Now what's nice with this is if you squeeze the bottle, allow the tube to sink to the bottom, if you continue to press harder, the bubble gets even smaller, demonstrating very nicely the principle behind how the Cartesian diver works.
Now, I'm going to squeeze the side of the bottle. What do you think is going to happen?
It's going to go up.
Right, something through the water, and the divers will, if I squeeze the edge, they sink. That's cool. Okay, we'll do that once more. I love this one. You squeeze the side and down they go. Now what I want to do is I want to show you, if you look very carefully on the inside, as you squeeze, the water level goes up inside the tube and then the diver sinks. Back up again. The water level goes up and then they sink. Did everyone see that?
Yes.
The water level goes up and then the diver goes down.
A way of extending this experiment is to get hold of tomato ketchup sachets which have got an air bubble inside. That means if you put them into a lemonade bottle and fill it with water, when you squeeze the side, the air bubble inside the sachet gets smaller and the sachet sinks to the bottom, and when you release the pressure on the bottle, it starts to rise to the surface again. The same principle, but they can take this home and demonstrate it to their families.
When you squeeze the side, inside that sachet, the air gets pushed upwards, so it becomes smaller, and the sachet should sink.
So do you get rid of the air?
You don't have to it must contain air. If it doesn't contain air, nothing will happen.
I've used these Cartesian divers before, but I find explaining the principle can sometimes be quite complicated. Have you got any ideas of how to explain it simply?
There's two ways of talking about this really. The first one would be to talk about as more water enters the tube becomes heavier and therefore sinks. Another way is to talk about the average density of the tube itself. As more water goes in, the average density increases, so becomes heavier than the water around it. Depends on what class you're talking to. A third possibility is to talk about the air inside being a buoyancy, providing upthrust. If you've got a smaller bubble, there's less upthrust, therefore the object sinks. As you allow the air to expand, it's got more upthrust, so it rises to the surface.
In general, I thought the responses to me asking them to explain what they saw were good. I would say that the general structure, showing them something, getting them to explain it and then come back at the end and explain it to the group, is one that I would use often for a revision lesson. Okay, so you four, what ideas have we got here then so far?
We've got when you squeeze the bottle, yeah?
Right.
Water level goes up and it goes up in the diver.
Right.
And so it's pushing it into a small space, which gives the diver more weight.
That's fantastic.
The unbalanced forces of the water and air makes the diver rise as the air has more upthrust than the water's gravity.
So you've got the idea about gravity, you've got the idea about air being bigger and smaller and upthrust. Combine them and you've got the answer.
With the marshmallows, when the air is being taken out, forces are unbalanced and the air pressure goes down, but the air bubbles inside the marshmallows stay the same, and it makes the marshmallows expand because the air pressure isn't pushing on them to make them smaller.
When you blow bubbles, you've probably noticed that they sink. Do it with helium though. What we should be able to demonstrate is that the gas, which is lighter than air, will rise up. Now, we use a balloon attached to a piece of ordinary laboratory hose, and there we see them rising to the ceiling. We've all seen helium balloons and know that they rise and they float in air, but seeing that and watching the bubbles rise up really links that in with the idea of floating and sinking. Inflate the balloon in the glass, and you can lift it off the table. If you use some washing up liquid or some bubble mixture, when you've got the glass with the balloon in the top, it really does show with everyday objects how air pressure is pushing on everything around us. If people can leave the classroom and really see science in the everyday things about them, then I think we've done our job well.